Okay, chapter 8, rotation. Uh, New life, if you will, but you will still find a lot of similarities between what we had for kinematics and dynamics for straight line and particle model versus the new model that we're about to discuss. It's not a particle model. Geometry will matter for rotation, but a lot of equations will look similar, and instead of linear quantities, you will see angular quantities, and you'll see a lot of connection between the two. So rotation, yeah, good news. Same laws apply, like the second Newton's law or conservation principles, and it's going to be new quantities that we're going to call angular displacement, angular velocity, angular acceleration versus linear quantities that we used previously for the previous 7 chapters. The analog of force is going to be the torque, and the torques are a little tricky, but still a straightforward parameter that you can easily calculate if you will use the line of action and moment arm approach, which I'll explain later, and just keep track of positive and negative values for clockwise or counterclockwise rotation. And instead of just mass, we will consider geometry, and the coefficient that is the connection between the geometry and the mass is what we're going to call rotational inertia. You don't have to remember any tables for those coefficients. I will provide those tables for the test. So just understand what it is, understand how you use inertia, and that's all that matters. So let's start with basic quantities. Remember, we did position, and then the change in position was displacement. So first of all, we have to define the axis of rotation because this is going to be your main parameter for rotation. Because if it's rotation, say, with respect to the center of a sphere, that's going to be one type of rotation. If the axis of rotation is, say, on this side, then rotation is going to be at a different level, and you have to define the axis of rotation for any extended object that we are considering. Once again, normal particles. Whatever is the object given, a sphere or a plate or, I don't know, some kind of a cylinder, that all matters. You have to keep track of the geometry of the object every time you discuss rotation. So define the axis of rotation. That's the first step. And then all points on a straight line drawn from that axis of rotation will move through the same angle at the same time. Consider those, say, point halfway between the center and the side, somewhere here. That's going to be theta. Theta is the angle that a point will move through. And consider another point on the same straight line moving on the outer edge of the object. What you can tell about the angle? The angle is going to be the same angle theta. So no matter how far you are away from the axis of rotation, every point on that same straight line will travel through the same angle theta in a certain amount of time. And this angle can be defined in radians, and it's not the same as degrees. For physics formulas, you have to, for rotational formulas, you have to think radians rather than degrees, and make sure your calculator is in radians mode. So angular parameters are with respect to this change in angular position, and angle is defined as the arc length, that L that you see in the diagram, over the radius between, it's the distance between the axis of rotation and the point on the outer edge of an object. So radian is the distance that the, radian is the angle that is defined as the arc length distance with respect to the radius for that particular rotating object. Let's take a look at an example for conversion between angles and radians. So this is the formula, arc length over the radius. And let's think about 360 degrees, which would be the same as one complete revolution. So one complete revolution corresponds to 360 degrees. So how do you convert that into radians? Well, what is the arc length? What is the distance that a point travels through in one complete revolution? That distance is called circumference. And how do you calculate the length of a circumference? It's 2 pi r. It is your connection for pi. Pi is 3.14 only because it is the ratio between the circumference and the diameter for any circle. This ratio is the same. So circumference can be solved from pi. So multiply by the diameter, which is double the radius. So 2 pi r is your circumference. And then you divide by r. See, it's L divided by r. So circumference divided by r. R cancels, and you're left with 2 pi radians. I'm pretty sure you've heard pi over 2, pi over 4. So all of those angles in radians, they correspond to certain degrees, and you can easily convert it between the two using this conversion factor. 360 degrees is 2 pi radians. 180 degrees would be pi radians, 90 degrees is pi over 2 radians, and so on. Now for rotational motion, you can't skip the 2 pi. You remember sine and cosine, they have the period of 2 pi. And for mathematics problems, you go one complete revolution and say, oh, we start over and over and over again. So you can ignore 2 pi in mathematics. You cannot do that in physics. You have to keep track of all the pi's that you travel through, because that will define your overall angular displacement. So do not reset theta to 0 after a full circle. That's what the node is all about. In mathematics, you would say 2 pi n, and n would be 0, 1, 2, 3, 4. In here, you have to count all those pi's and keep the number of pi's handy for all of your calculations. So it was linear displacement, change in position, initial, final, takeaway, initial. Now take a look at the formula for angular displacement, and you'll see that it's the same thing. The only difference is that position was in vector form, and for angular displacement, you don't see any vectors on top. You only have to keep in mind positive or negative direction, and clocks are negative by default, so clockwise motion would be negative motion, and counterclockwise that you see on this diagram is positive. So angular displacement, it's like your linear displacement, but with angular parameters in radians. So if you were at position corresponding to an angle theta sub 1, and you moved from theta sub 1 to theta sub 2, then there is a change in position, and delta theta is what we call the displacement, angular displacement from initial position to final position in radians. So yeah, be careful with direction of rotation. So clockwise direction, see at CW direction, that's clockwise, and CCW direction means counterclockwise, that is positive direction. Why is it so? Well, it's just a convention, and For some reason, we don't like clocks. Clocks are negative. That's good not for only angular displacement, but also for other parameters that you see, the torque, the angular velocity. Any clockwise rotation is considered negative. Any counterclockwise considered positive. So let's take a look at a disk that rotates about its central axis like a merry-go-round. Pairs of values for its initial and final angular positions give a negative angular displacement. Once again, negative angular displacement means that the change between the final and initial is negative. That means you'll get a negative delta, negative change. That is your negative angular displacement. So you were at -3 radians. Now you are at +5. Final takeaway initial, 5 takeaway -3. That's a +8. So option A, not good, because you're going to get a positive angular displacement. From -3 to -7, it's -7, take away -3. That's -4 radians. That's a good value for a negative angular displacement. So option B, -4, that satisfies the condition for negative angular displacement. Last option, from 7 to -3 radians. -3 take away 7, that's -10. Also a good negative value for the angular displacement. So first one is +8, second is -4, and the last one is -10. That's the angular displacement. From angular displacement onto angular velocity, remember it was linear velocity that was the displacement with respect to time. Guess what? It's the same idea for angular velocity. It's the change in angular position, which is your angular displacement with respect to time. The only difference that it used to be meters per second. Now we're talking radians per second. So at moment t1 you were here, at moment t2 you are there. This is your angular displacement, and you have to divide by the amount of time that it took you to get from here to there, and that would be your average angular velocity. And then we had acceleration, which was change in velocity with respect to time. Same thing here. It's now angular acceleration, and it's angular velocity final takeaway, angular velocity initial with respect to the moment of time that it took you to get from omega-1 to omega-2, and you get your delta omega delta t, so change in angular velocity with respect to the moment of time, the interval of time. Units are radians per second, because it was radians per second for angular velocity, and then you have to divide by time once again. So divide by time once again. You have to say radians per second, and that makes it second squared. Now all the particles are locked together. Remember that we're talking about a solid object. We are not talking fluids yet. We will discuss fluids in later chapters. For now, it's mechanics of a solid object. So consider all points on the body going through the same angular displacement with the same angular velocity, and therefore angular acceleration is the same for all the objects, all the points that make up the object. Okay, this was the definition for radian. Once again, the arc length that the point goes through with respect to the radius. And you can multiply both sides by r, and that's what you're going to get. Your arc length is radius times the angle in radians. And then you can substitute your connection between linear and angular parameters into definition of linear velocity. And you will see that with delta L being r theta, so r delta theta, radius stays constant, you get to the formula where the linear velocity is the radius times the angle in theta with respect to time. And what is delta theta delta t? It is the definition for delta theta to delta t is the definition for angular velocity. So all of a sudden, your linear velocity gets the connection to angular velocity. So v is r omega. And it turns out that this interconnection is very important, and a lot of problems will be solved using this interconnection. And I can even tell you more. It's not good only just for the velocities. It's also a working connection for accelerations. So using the same strategy, where is it? Yeah, here we go. Using the same strategy, you will arrive to a conclusion that linear acceleration is r times the angular acceleration. So linear velocity is r times angular velocity, and linear acceleration is r times angular acceleration. You have to keep those connections in your mind. And every time a problem is dealing with linear motion and rotation of some kind, you can connect those two motions with those equations. So V is R omega and A is R alpha. So linear speed is proportional to the angular speed of that body. And I'm pretty sure you've noticed that the closer, like let's say you're in a carousel or the merry-go-round, and if you're close to the center, then you're moving rather slowly. And if you're further away from the rotational axis, then you're going to move pretty fast. And that's the connection that this formula explains perfectly. The more the r, the more the radius, the more linear velocity you're going to get with the same omega. Remember, omega is going to be the same for every point, but your linear velocity will be proportional to the radius. So the further away you are from the center, the faster you're going to move as your linear velocity, considering the linear velocity. So yeah, objects further from the axis of rotation will move faster. You see that the magnitude of this vector is less than the magnitude of the vector on the outer edge because of this relationship between linear velocity and angular velocity. So any change in velocity, that's what we call acceleration. And remember that v is now r omega. So because v is r omega, you can use it for your definition for linear velocity and replace linear velocity with r omega. And all of a sudden, delta omega to delta t is how we defined angular acceleration. Angular acceleration is delta omega to delta t. So your delta omega to delta t becomes just average angular acceleration. And once again, your linear parameter gets the connection to angular parameter. Just multiply by the radius, and that's all you need to do. A lot of problems will use this connection and v equals r omega connection as well. So make sure you have them handy for your problem solving activities. Sometimes it's the angular parameters that are given, and you can figure out the linear parameters from those interconnections. Sometimes it's the other way around. the point is, if you have set of linear parameters, you can easily figure out the angular ones and vice versa. That's very handy for problem solving. Okay, for rotation, you definitely want to recall your centripetal acceleration. And now see how v is r omega. Your linear velocity is replaced with that connection to angular parameters, and you have to square r and omega. So r squared over r, one radius is canceled, but the other one stays. And omega squared just enters the connection. So instead of thinking v squared over r, you can think omega squared times r. And this is just a result of previous definitions and calculations. You can use it in your formulas without any proof, because this is pretty much the definition for centripetal acceleration. You must use radians. See how it's in red and bold and exclamation marks? Do not forget that formulas for rotation are in radians. You have linear displacement, meters, velocity, meters per second, acceleration in meters per second. And then for angular parameters, it's going to be radians, radians per second, and radians per second. Frequency. Recall frequency. We discussed frequency as number of something per unit of time, which is the inverse of a period. So it was 2 pi r divided by v. Now instead of v, you have omega, and your r gets canceled once you think radians. And with that, you have your frequency as angular velocity over the magic number pi times 2. And units are hertz, which is the inverse of a second. So frequency is still there. If frequency is given, you can figure out how fast you go in terms of angular velocity right away. If you need period, period is still the inverse of a frequency. So 2 pi over omega, that would be the period for your revolution. Oh, which is exactly what the next slide says. Period is the time that it takes for one revolution, which is the inverse of the frequency. Once again, frequency is number of times per unit of second, and period is the number of seconds for one revolution. So if it's omega over 2 pi for the frequency, then it's 2 pi over omega for the period. It's just the definition of a period. Remember, period is distance over the speed. Distance is 2 pi r, speed is v. Convert your v to r omega, and r cancels, and you're left with 2 pi over omega. Okay, here we go. Cockroach rides the rim of a rotating merry-go-round, so just on the edge of the merry-go-round. And omega is constant. Omega is constant. Does the cockroach have radial acceleration? Okay, for radial, it's along the radius. It's your centripetal acceleration if you're confused on the terms. Remember, we have tangential acceleration, and you call it linear acceleration, and then you have radial acceleration, and that's what we call centripetal. So radial means centripetal, tangential means linear. So for radial acceleration, it's definitely a yes, because we're doing circles. And for every circle, for every curve, there is a change in direction for velocity. And you do get centripetal acceleration. So the answer is yes. I'll take a look at the previous diagram. You do have centripetal, or see how it's radial, R stands for radial. And then you have linear acceleration if you're speeding up or slowing down. Are we speeding up or slowing down here? No, we say omega is constant. That means no change in speeding up or slowing down. It's just no linear acceleration. That's why the answer is no. Now omega is decreasing. Does the cockroach have radial acceleration? Still, we're still doing circles. We're still doing change in direction. That means there is centripetal, or you call it radial acceleration. And how about tangential acceleration now? Well, now we do have change in omega. That means change in velocity. We're slowing down. Speeding up or slowing down, there's definitely a yes for tangential acceleration. See this acceleration? This would be speeding up, but if tangential acceleration is opposite to rotational direction, you will get a slowing down process. So once again, centripetal is for direction, change in direction, and it's always there when you do circles. And tangential is speeding up or slowing down, and it says uniform, then no speeding up, no slowing down, no tangential acceleration. So nothing here because omega is constant, no speeding up, no slowing down. Yes, for this case, because omega is changing, so you do have speeding up and slowing down. And there's always centripetal acceleration because you're doing circles. Okay, let's take a look at our favorite equations from kinematics. You can see that for kinematics and straight line motion, you got v equals v sub 0 plus at. And for rotation, you should admit that it's the same result. Linear velocity at any moment of time, angular velocity at any moment of time, linear initial velocity, angular initial velocity, plus linear, or you say tangential acceleration, plus angular acceleration. And t is just the moment of time, which is the same time as before. Time goes the same way for both x and y axis, for the same kind of motion. It's the same moment of time, which is very convenient. For the change in position, it's the initial velocity times time plus at squared over 2. For the angular change in position, it's the angular initial velocity times the time plus 1/2 angular acceleration times t squared. So exactly the same set of equations, just flip from linear parameters to angular parameters, replace them, and that's all you need to solve all the rotational problems, or rotational kinematics problems. Okay, so before we hit dynamics, a few words about rolling. What is rolling? Well, think about you being just a bystander on the sidewalk, and then you see bicycle wheels. So someone's riding a bicycle. What do you see for bicycle wheel? You see the bicycle wheel will rotate with respect to axis of rotation O with a certain angular velocity, and the bicycle will travel in a certain direction. So there is a straight line motion in a certain direction. So the center of mass of the bicycle wheel will actually move in a certain direction. So you have a combination of two types of motion. First of all, rotation with respect to a certain axis, and translational linear motion in a certain direction when all the points on the bicycle move in a certain direction. You're going to add up those velocity vectors as vectors. And what do you see? You see that momentarily the bottom point is at 0. It's not moving. The center point This is your center of mass. Only the translational motion, so same as just pure translation. And the topmost point has v plus another v, so it's double the velocity, and it's going to move very fast. Well, if you ever notice how wheels rotate, you've probably noticed how there is a different amount of motion between the topmost point and the bottom point. Well, if not, then just consider adding those two vectors, rotation plus translation, and that's the resulting vector diagram for such motion. So every time you solve a problem on rolling, do not forget to consider both types of motion, translation and rotation. Okay, now let's move to dynamics. And for dynamics, we need forces. And the analog of a force for rotational motion is what we call torque. And it is the force that we need to produce some kind of an acceleration. And we still need the force to start rotation. Rotation cannot start out of nowhere. You need a force to produce that kind of motion. And for the torque, you have to think two things. The force, the magnitude of a force, like how much of a force you have, and where and how it is applied, which is the difference between dynamics of a point versus the dynamics of rotation. So you have to keep in mind the geometry of the object and where the force is applied. Now, the definition for torque, first of all, it's a product between two vectors. You have a position vector that connects the axis of rotation to the point where the force is applied, multiplied by the force as a vector. And that's not the best way of calculating torques. Because only the tangential component causes the rotation. You can't really produce anything with any rotation with the tangential component. Excuse me, with the radial component of the force, that's tangential, and that's the radial. That's along the radius. This force produces no rotation, only the tangential component acts for that. And you really want to focus on this kind of an approach to calculate the torques. Let's see what's going on here and what's the difference. First of all, the difference is you have some trigonometry going on here, the sine of an angle, and see how it's not the angle between the two vectors that we discussed, but the other angle. And no angles whatsoever to consider here. All you need is you have to draw what we call the line of action. You can see the line of action shown through that force. So you draw a force and you extend this force in both directions, up and down, and that's what we call the line of action of a force. Once again, this is the original force. You extend it up and down, and you draw this line. This is the line of action for that force. And then you have to find the smallest distance between the axis of rotation and the line of action. And the smallest distance is always the perpendicular. It is the line that is perpendicular, 90 degrees angle, between the line of action and the axis of rotation. This smallest distance is what we call the moment arm. And your alternative approach to calculate the torque would be the magnitude of the force by itself, no sine, no cosine, just the force, F, times the value of the moment arm. And if you look closely, you'll see that the moment arm is actually opposite to that angle that we discussed earlier. So it is a natural sine of that angle that's going to enter your calculations. And technically, you're still talking about force multiplied by the sine of an angle and the same position vector. But this little approach, if you can calculate the moment arm without doing the sine of angle, which you normally can, sometimes it's just given to you specifically, sometimes you can figure out from the geometry of the object itself. If you can do that, you just multiply this moment arm by the force itself, and boom, you got the torque. One last thing, don't forget the torques can be positive or negative. So this particular force would create rotation, but counterclockwise. So the torque would be positive. Let's say this force was applied here and going downward, then it would be a negative torque because it would have caused negative, clockwise rotation. So line of action is the first thing. Extend your force up and down, and you will get this line of action for this force. And the smallest distance between axis of rotation and the line of action is your moment arm. So yeah, moment, or so yeah, sometimes you will hear the word lever arm. Some books actually have it as lever arm. It's the same thing. Moment arm or lever arm, it is the distance, perpendicular distance from the line of action to the axis of rotation. So smallest distance. Units. Units are what? You have force and you have distance. So it's Newton and meters. And remember, we had newtons times meters for joules, and that was good for energy and work done. No more of that. It's only Newton meters as is. Do not say joules. Joules are reserved for energy and work, and Newton meters are for torques. So unit of torque is Newton meter. Yeah, torque is not energy, even though the units are the same, but please do not say joules for torques, and do not say Newton meters for energy or work done. Newton meters are torques, and joules are work and energy. The more the moment arm, the easier it is for you to start rotation. Real life example is try to rotate the nut that connects the wheels to your car. The more the moment arm, the easier, the less force is needed to start rotation. Yeah, let's take a look at this example. F sub A, this is how you open the door naturally without even probably noticing it. But this is the line of action, up and down. And the shortest distance between the axis of rotation and the line of action is just the door itself. And this is how you get the maximum torque. F sub A times the length of the door, and you have the maximum torque produced by force F sub A. If you'll try to push the door at an angle, see how the line of action changes from being vertical to being slanted, being like an inclined plane. And the shortest distance, the moment arm, becomes less. It was the total length of the door, R sub A. Now it's going to be R sub C, which is a less of a moment arm for you to use. So with the same force, multiplied by less of a moment arm, you're going to get less torque. So it's going to be much harder for you to open the door if you push it from an angle. And then how about you start rotating the door with the force F sub D? Well, chances are you will never open the door with that kind of a force. Why is that so? Because the line of action, you can see the line of action, crosses the rotational axis. And what's the smallest distance then? The smallest distance between the line of action and the axis of rotation is just 0, because the line of action crosses the axis of rotation. It's a 0 moment arm, and moment arm multiplied by any kind of a force, if it's a 0 moment arm, it's just a 0 as a product. So the torque created by F sub D is 0. So you can push as hard as you want, but the door will never open. It will never rotate and become opened. The only way to open the door is when you have some tangential component. Any radial component will not create any rotation. And that's why the diagram shows it all. Every time your line of action crosses the axis of rotation, moment arm is 0 and torque is 0. Yeah, that's what we have for positive and negative. Remember, clocks are negative. Clockwise rotation, negative. Counterclockwise rotation is positive. Of course, multiple forces can act on the system, and then you have net torque. Remember, we had net force for the second Newton's law. Now it is net torque. That's what will be the second Newton's law for rotational dynamics. Okay, all forces have the same magnitude. Let's rank them according to the magnitude of the torque, greatest first. Well, it's not greatest first. Let's just go one by one. What do you say for F sub 1? That's the line of action. And that's the pivot point. That's the axis of rotation. So it's F sub 1. And the smallest distance between the line of action and axis of rotation is what? 20 units from 0 to 20. That's 20 F sub 1. That is the value for the torque. Is that torque positive or negative? Well, rotation is going to be in the counterclockwise direction. So the torque from F1 is positive. Counterclockwise is positive. Now, how about F sub 2? Well, the line of action, that's how it is. You extend the line in both directions. And you can see how this line crosses the pivot point. It crosses the axis of rotation. So the smallest distance between the axis of rotation and the line is just 0. So moment arm is 0. So the torque is 0. F sub 3, that's the line of action. That's the axis of rotation. The smallest distance is 40 take away 20. So you have 20 units for the moment arm. So it's 20 times F sub 3. That's the torque. Is it positive or negative? Well, the kind of rotation is clockwise from F sub 3. So the torque is negative. F sub 4, that's the line of action. Extend it up and down. And the smallest distance between this line of action and axis of rotation would be somewhere here. This is the moment arm, which is going to be less than 20 times the F sub 4. So F sub 4 will definitely be less than F sub 3, but still in the negative direction. So F sub 3 is greatest with respect to F sub 4. But F sub 2 is just 0, so F sub 2 is even less. And how about F sub 5? That's the line of action. And you can see the line of action crosses the axis of rotation. It crosses the pivot point. So what's the moment arm? The moment arm is 0. The smallest distance between line of action and axis of rotation is 0. So torque from F sub 5 is 0. So F sub 2 is 0, F sub 5 is 0. F sub 1 and F sub 3 are the same, but opposite in sign. And F sub 4 is less than F sub 3, and it's a negative sign. Two forces are applied to a stick. Only one force is shown. The other force is perpendicular and applied at the right end. If the stick is not to turn, what's the direction of F sub 2? Well, you do have some torque, F1 times this moment arm, and it's the torque in the counterclockwise direction. That's what's given, so some positive torque. So in order for that stick not to turn, you need the torque in the opposite direction. That means you need some clockwise rotation. So the force must be downward. Now, how do you compare the magnitudes? Should that magnitude be greater than F1 or less than F1, or is it the same? Well, that depends on the moment arm. So you have the moment arm for the positive torque being much less than the moment arm for the negative torque. So the more the moment arm, the less of a force you will need to produce the same torque. Once again, smaller moment arm, greater force, greater moment arm, smaller force. And its force downward because that's how you would produce clockwise direction, which is a negative torque. And F sub 1 produces counterclockwise motion, and that's positive torque. So F sub 2 points downwards for the opposite direction of a torque, and it has less magnitude because it has greater moment arm, or you say lever arm. Let me get a sip of water and we'll talk dynamics. So for dynamics, we need the second Newton's law. And this was the second Newton's law with constant mass back in the days with linear parameters. Now, recall the connection between linear parameters and angular parameters for acceleration. It's r times alpha. So instead of linear acceleration, I want r times alpha. And from here, I want to multiply both sides by r. Can I do it? Yeah, why not? It's a perfectly legal thing to do. Multiply both sides of the equation by a certain parameter. You're not going to change the truth of the expression. And what you see on the left side after the multiplication is what we defined as torque, r times f, r times f. So left side becomes the torque when the sine of the angle is just 1. So for the sine function, you need 90 degrees, and you get the maximum value. And what we have on the right side of the expression, it's the mass. R goes squared, and alpha is still there. So this is your second Newton's law for a point mass, a single point mass, which is at a certain distance away from the axis of rotation, multiplied by the change in angular velocity that this torque produces. And, well, this was a single point mass scenario. How about the general case? The general case means you have to add up all the torques acting on the system. That becomes the net torque. And then you also have to add up all the pieces that make up the object. This Greek symbol means the sum. So sum of all the torques is sum of all the point masses a certain distance away from the axis of rotation, multiplied by the angular acceleration. And the coefficient that represents the mr squared, the sum of all the mr squared that make up the object, is called rotational inertia. Sometimes you'll hear moment of inertia, so rotational inertia, moment of inertia. Either way, this capital I is your coefficient for the second Newton's law, and that replaces the mass. It was just mass for the particle model. Now it's not a particle, it's an extended object made up of different atoms and molecules, which are located a certain distance away from the axis of rotation, and the way to represent that for calculation is to consider rotational inertia rather than the mass. So it was F equals ma. Now it's not F, it's the torque, and it's not mass, it's rotational inertia, and it's not linear acceleration anymore, it's the angular acceleration. So this is your second Newton's law for rotation. Every time the problem represents some kind of rotation, you can use this law as your general equation to start solving for missing parameters. Yeah, you can see that rotational inertia of, say, a disk is not the same as rotational inertia of a cylinder. The cylinder will rotate in a different way compared to a disk, even if the forces and the torques are the same. You would still get a different kind of rotation because geometry now matters. You will get a different coefficient for rotational inertia. That's the table that I'm talking about. See how for a sphere with a certain radius, your rotational inertia is 2/5 mr squared. And for a certain rod, with respect to the central axis, it's 1/12 ml squared. L is the length of the rod. See how it's the same rod, but now the axis of rotation is not through the central point, not through the middle point, but rather the side, or one of the sides of the rod. And what do you see? You see that rotational inertia changes from 1/12 to 1/3. And if you ask me why is that so, you have to go to calculus class and consider the calculation of a center of mass, and that will lead you to those coefficients. So the short answer is because the calculus says so. The calculus of a center of mass tells you the rotational inertia. And if it's a plate, then you can see that the coefficient is something else as well. So you don't have to remember those coefficients. This table, you can find it in the textbook, and you can, I will provide you this table as a set of formulas for the test. So all you have to do is just see what kind of object is given, and then consider a certain coefficient for that rotational inertia. You don't have to derive those coefficients. So F equals ma, but it's not the force, it's the torque now, net torque. It's not mass, it's rotational inertia. And it's not linear acceleration, it's angular acceleration. This is your main equation for dynamics of rotational motion. You can see different masses rotating with respect to this axis at a certain distance away from that axis. And what do you see? You see that the torques produced by those masses are all equal. Because if it's mr squared, then mass is 36, r is the radius. So 1 meter, 1 squared is 1. So 1 times 36, the torque is 36 Newton meters. Now you have 9 kilograms rotating 2 meters away, mr squared. So it's 9 times 2 squared. Sorry, the headset turned off. So 9 times 2 squared. 2 squared is 4. 4 times 9 is 36 again. So it's 36 Newton meters for the torque created by this mass. And the last option is 4 kilograms times 3 squared. 3 squared is 9. 9 times 4 is 36 Newton meters again. So masses are different. Distances for rotation with respect to rotation axis are different, but the torques are the same. So torques produced by this rotation and this rotation and this rotation are all the same. It's not just the mass that matters. it's how the mass is distributed through the object that matters as well. So you have to draw the forces and show the axis of rotation. For calculating the torques, once again, I suggest you draw the line of action, find the moment arm, and multiply the moment arm by the force itself, rather than bothering with sine of an angle between the vectors, and it's a very tricky approach. Do not do that. Do the moment arm times the force itself. Chances are you will have rotational motion, so you can do the Newton's second law for rotation, which is right here. This is your general equation to consider. If rotational inertia is not provided, you need to find it, so you look it up in the table. Or you have to solve for it, probably. Doesn't matter. You will need it, so either way, either you solve for it or you have to find it in the table. And for the most challenging problems, you would also use F equals ma on top of rotational motion and conservation principles as well, because everything that we discussed so far is the foundation for the next topics. Remember, we started with just basic kinematics of a particle. It's not a particle anymore, and it's not even a straightforward motion, it's rotation. But Newton's second law is still there, conservation principles are still there, so you are expected to use proper tools for all of those problems. And if it's rotation, go ahead, use angular parameters and replace your F equals ma with the torques, or maybe use them both. If, say, you have rolling, remember the bicycle wheel, you will use both because it's both rotation and translation, the linear motion. Yeah, see, it says see examples in the textbook, step-by-step solution, because you will find some of those in the test problems. So go check the textbook for those examples. Okay, rotational kinetic energy. Remember, it was 1/2 mv squared for linear motion, translational motion. Guess what? 1/2 stays, and instead of a mass, you go with rotational inertia. And instead of linear velocity, you go with angular velocity. So nothing has changed here. The formula by itself has the same parameters, but instead of linear parameters, you now use angular parameters. So worst case scenario, you have rolling, which means 1/2 mv squared. And see how it says the center of mass. That's one of the important pieces of the puzzle, why you need the center of mass in the first place. And then the center of mass for rotational part. Your bicycle wheel moves forward and it also rotates. And for the total kinetic energy of two types of motion, you have to add those kinetic energies together. Remember the work done? Work done was force dot displacement. So force, displacement, and the cosine of angle between the two. Guess what? Same thing for calculating work done by a torque. Instead of force, it's now torque. And instead of linear displacement, it is now angular displacement. So torque does work, and for a certain change in angular position, the work done is the torque times the change in that position, change in in angular position. Remember change in kinetic energy work done theorem? Same thing still applies, but your kinetic energy, it's not mv squared 1/2 mv squared anymore. It's 1/2 I omega squared, because mass is replaced with rotational inertia, and linear velocity is replaced with angular velocity. For momentum, remember linear momentum, mv. Now we got angular momentum. Instead of a mass, you got rotational inertia or moment of inertia. And instead of v, linear velocity, you have angular velocity, omega, radians per second. Remember radians, not degrees. And remember the second Newton's law? Change in momentum with respect to time. That was the net external force. You need a net external force to change the object's momentum. Guess what? You're going to need the net external torque to change the object's angular momentum. So change in linear momentum, net external force. Changing angular momentum, net external torque with respect to time force. And it's also conserved. Good news, angular momentum is conserved the same way as linear momentum was, which allows you to solve all the collision problems when you have some kind of rotation. So you have one rotating disk, and then another rotating disk falls on top of it. You can easily say I omega equals I omega before the collision, after the collision, or 1, 1, 2, 2, and this quantity is conserved. Be careful, it's not necessarily 0. It means is no change. It can be 5 and it stays at 5. It can be 50 and stays at 50. Not necessarily 0. Constant doesn't mean 0. It can be any other value. And this value cannot change before the collision versus after the collision. Yeah, let's take a look at some applications. If you are familiar with figure skaters, they rotate with respect to the axis, the vertical axis that their body represents. And if they stretch their arms outward, that means distribution of mass is quite significant. Like a lot of mass is outward, away from the axis of rotation. So the rate of rotation is not as much compared to when the figure skater brings her arms next to the axis of rotation. They bring their arms next to the body, there's the center of the axis of rotation, and they start spinning much faster because rotational inertia decreases. I goes down, omega goes up, because the whole product stays constant. You extend your arms, I goes up, omega goes down. You bring those arms close to the axis of rotation, I goes down, omega goes up. But the product is still the same. Same thing with the diving. See how hands are stretched out, so a lot of mass is away from the axis of rotation, and then during the rotation process, the diver groups her body and tries to create a setup when everything is really close to the axis of rotation, and she starts spinning like crazy. They can do 3 or 4 complete revolutions before they enter the swimming pool. So the only way to make those 3 or 4 revolutions possible in that short time is to group the body all the way close to that center of rotation, the axis of rotation, so you start spinning faster. So angular velocity vector points along the axis of rotation. Direction is found using right-hand rule. We're not going to do any of right-hand rules in this level, but think about a right hand and thumb shows the direction for angular velocity if you curl with your fingers in the way that rotation happening. That would be the vector for angular velocity and therefore angular momentum. For all of your calculations here, all you have to do is just keep track of positive or negative. That's enough. Just make sure that for your clockwise results, you say negative, and counterclockwise kind of rotation, you say positive. That's all I'm asking you for. Okay, that's it for the lecture. Stop the recording and let's do the classroom discussion.